Next, we will look at the mechanism of electrophilic aromatic substitution in benzene, which is Friedel alkylation. So for Friedel alkylation, it involves three cases. So I will show you for tertiary haloalkane first. This is an example of benzene reacted with tertiary haloalkane in the presence of Lewis acid catalyst. We will get this product. We go to step 1, still same formation of electrophile, but now our electrophile is Lewis acid base complex or carbocation ion. What happened at step 1? Our tertiary haloalkane will reacted with the Lewis acid. So the arrow is from this lone pair to this aluminium, and what we will get here is this one. You just copy back from your haloalkane. This is from haloalkane, and it will attach to AlCl3, and now it will become the positive charge. And then class, this ion is unstable and it will break the bond between C and Cl. So the next arrow is between this bond which break, and 2 electron will go to the Cl, and this one will be break, and we will get this AlCl4 minus, and this side is the carbocation ion. So this is our electrophile in this mechanism. Okay, step 2 is a formation of uranium ion. So we have benzene ring will react with our electrophile formed from the previous step. So what we will get here is we will have uranium ion. So the arrow is from the CC double bond of benzene. It will attack the carbocation ion, and one side of the CC double bond will break, and it will become positive charge at one carbon, and another carbon will attach the alkyl group from the carbocation ion. So like previous one, here we'll have a resonance structure where this CC double bond or pi electron will move to this side. Okay, not the arrow must be to the side of your benzene. Now the CC double bond has become here and positive charge at this carbon, and arrow from this CC double bond, this electron will move to this side. We will have another structure of uranium ion, and all of these three structures are called as resonance structure. So that is step 3. That is step 2. Step 3 is loss of H+. We will move or remove H+ from the hydrogen of this carbon. So what we will involve in this step is AlCl4 minus formed from first step. So this chlorine, we have lone pair here, it will attack the H, and this CH bond will break, and 2 electron will go to this side, not to this C+, that is to this side, and we will get back our CC double bond in the ring, and the side product HCl and the AlCl3, which act as Lewis acid catalyst, will remain as AlCl3. So that is the mechanism for the tertiary haloalkane. Now look at secondary haloalkane. This is example of secondary haloalkane reaction. We will start with step 1, formation of electrophile. Our electrophile is Lewis acid base complex or carbocation ion. Involved in the first step here is the haloalkane, secondary haloalkane, and the AlCl3, the Lewis acid. So same as previous mechanism, lone pair will attack the AlCl3, and we will have this complex Lewis acid base complex. You just copy back your haloalkane that attached to AlCl3, and this ion is unstable. It will break the CCl bond. What we will have here is we will have carbocation ion, and also AlCl4 minus. This side will form the AlCl4 minus, while this side will form the carbocation ion. So this is the electrophile that will be used in the second step. Now we go to the second step. It is the formation of aromatic ion. So benzene will react with your electrophile. So the arrow must be from CC double bond. It will attack the C plus or electrophile. What we will have here is one side of our benzene, CC double bond will break, and let's say I choose this side. So this carbon will attach the alkyl group, while this carbon become the carbocation ion. And same as previous one, we will have resonance structure, whereas this this pi electron will move here, we will get the second structure. This pi electron move here, we will get the third structure. So you have to draw the resonance of this aromatic ion. The third step is loss of H plus. The H plus that will be lost is this H that attached to the carbon at the neighboring of the aromatic ion. So what will involve in this step is AlCl4 minus from the previous step. So the Cl that contain lone pair here, it will attack this H, and this CH bond will break, 2 electron will go to this side, and we will get back the CC double bond or conjugated double bond in our benzene ring. And we will have our AlCl3, the Lewis catalyst, Lewis acid catalyst, and HCl as our side product. Okay, when Cl attack H, this AlCl will also break. That's why we will have the side product HCl, and AlCl3 will remain as AlCl3. Okay, for primary haloalkane, this is example. We have primary haloalkane react with benzene. Okay, first step is also the formation of electrophile, the Lewis acid-base complex or carbocation ion. And our primary haloalkane will react with the Lewis acid. So same as previous mechanism, the arrow from chlorine, it will attack AlCl3, and the haloalkane will attach to your AlCl3, forming the Lewis acid-base complex. Okay, class. But for this primary haloalkane, this Cl plus will not break with C. It will remain as this Lewis acid-base complex, and this species will involve in the step 2. Now we look at step 2. Benzene will attack the Lewis acid-base complex. So it will attack the carbon here. Look at the arrow. This arrow, it will attack the carbon of the Lewis acid-base complex. What we will get here is CH2CH3 also will attach to this carbon, but when this CC double bond attack this carbon, this CCl will break. So 2 electron will go here, and this species will be break from the alkyl group. This alkyl group will attach to benzene, same as previous mechanism. We will have our resonance structure. This pi electron will move here, we get the second structure. This pi electron move here, we get the third structure. And AlCl4 minus from the breaking of CCl bond. Now we go to step 3, loss of H plus. This H plus will be removed, and the one that involved in the step 3 is AlCl4 minus. Cl will attack this H, this bond will break, 2 electron will move to this side, and we will get back our conjugated double bond in benzene ring plus AlCl3 and plus HCl. So that is the mechanism of primary haloalkane.